You know that the human ear cannot hear sounds of all frequencies. The range of frequencies of sound waves to which the human ear is sensitive is known as the audible range. This audible range is normally from 20 Hz to 20,000 Hz. In the same way, the human eye is also not sensitive to all frequencies of electromagnetic waves. The electromagnetic waves to which the human eye is sensitive is called visible light. The approximate frequency range of visible light is 4 × 10⁻14 Hz to 7 × 10⁻14 Hz. In terms of wavelength, the range of visible light is 700 nanometer to 400 nanometer. All electromagnetic waves, including light waves, travel in vacuum with an approximate speed of 3 × 10⁸ meter per second. This, in fact, is the limiting speed of nature. That is, in a vacuum, no other wave or particle can travel with a speed that is greater than the speed of light. When the size of an object with which light interacts is very large compared to its wavelength, we can treat the light traveling in straight line. This straight path of light is called a ray of light. A bundle of such rays together is called a beam of light. The study of different optical phenomena by treating light as rays is known as ray optics. In ray optics, the propagation of light through an optical media is studied by tracing these light rays. Let us first observe the path of light when it falls on an interface of two transparent media. When a beam of light is incident on an interface separating two transparent media, it is partly transmitted through the second medium and partly reflected into the same medium. The light ray that falls on the interface of the two media is called an incident ray. The light ray that is transmitted through the second medium is called a refracted ray. The light ray that bounces back to the first medium is called a reflected ray. The angle between the incident ray and the normal is called angle of incidence, I. The angle between the reflected ray and the normal is called angle of reflection, theta. The angle between the refracted ray and the normal is called angle of refraction, r. You may have observed that when light rays enter the second medium, they deviate from their usual path. This phenomenon is known as refraction of light, and you will study this in detail in subsequent modules. If the second medium is opaque, most of the light reflects back to the same medium. When the surface is smooth, reflection takes place at a definite angle and is known as specular reflection. If the surface is rough, reflection is called diffuse reflection. Whether the reflection is specular or diffuse, it was experimentally found that the reflection of light follows two laws known as the laws of reflection. According to the first law, the angle of incidence I is equal to the angle of reflection theta. The second law says that the incident ray, the reflected ray, and the normal to the surface at the point of incidence all lie in the same plane. These laws of reflection are valid in the case of curved surfaces also. We need to draw a normal to the surface of point of incidence. To measure the angle of incidence I and the angle of reflection theta. This can be done by first drawing a tangent to the curve at the point of incidence, and then by drawing a normal to the tangent at that point. Now take a look at the picture. We can see the image of hilltops on the smooth surface of water. It is like any image we see in a plane mirror. But what is an image? When a point object O is placed in front of a plane mirror, rays from the object after falling on the mirror get reflected and form a diverging beam. If these diverging rays are extended backward, they meet at a point, say I. That is, the diverging beam of light appears to be coming out of a point I behind the mirror. This point I is the image of the point object O. This is a virtual image because after reflection, the rays appear to be diverging from that point. If a converging lens is placed between the object and the mirror, light rays, after passing through the lens, form a converging beam. When this converging beam of light is incident on the plane mirror, after reflection, they converge to a point and form an image IR. Since the image is formed by actual convergence of light to a point, it is known as a real image. Hence, we have two types of images, real and virtual images. When light rays from an object, after reflection or refraction, actually meet at a point and form an image, it is called a real image. If the light rays after reflection or refraction appear to diverge from a point, the image is called a virtual image. You have already learned about plane mirrors. But mirrors are not always flat. Take a hollow glass sphere and cut a small portion out of it. The inner hollow surface of this cut portion is called the concave surface, and the outer bulging surface is called the convex surface. If the convex side is given a silver coating, and the smooth concave surface acts as a reflecting surface, the mirror is called a concave mirror. On the other hand, if the concave surface is coated in silver, and the smooth convex surface acts as a reflecting surface, the mirror is called a convex mirror. Let us define certain terms relating to spherical mirrors. The center of the sphere of which the mirror is a part is called the center of curvature, C. And the radius of the sphere is the radius of curvature, R. The geometrical center of the spherical mirror is called its pole. The imaginary line passing through the pole and the center of curvature of a mirror is called the principal axis. If rays of light from an object make small angles with the principal axis and incident at points close to the pole. The rays are called paraxial rays. Paraxial rays, parallel to the principal axis, after reflection from a concave mirror, converge to a point on the principal axis. This point of convergence is called the principal focus of the concave mirror. In the case of a convex mirror, such parallel rays of light after reflection appear to diverge from a point on the principal axis, known as the principal focus of the convex mirror. When parallel rays making a small angle with the principal axis are incident on a concave mirror, the rays converging to a point on a plane that is normal to the principal axis and passing through the principal focus. This plane is called the focal plane. The distance between the pole and the principal focus of a mirror is called its focal length and is denoted by f. Now let us derive a relationship between the focal length f and the radius of curvature r of a mirror. Consider a ray of light parallel to the principal axis incident on the mirror at a point M. We know that the ray of light, after reflection, passes through F in the case of a concave mirror and appears to diverge from F in the case of a convex mirror. Since C is the center of curvature of the mirror, CM is the normal to the mirror at M. If the angle of incidence is theta, then the angle of reflection is also equal to theta. Let MD be the perpendicular to the principal axis through M. Using basic laws of geometry, we can write that angle MCD is equal to theta and the angle MFD is equal to 2 theta. From the triangle MCD, tan theta is equal to MD by CD. Let this be equation 1. And from the triangle MFD, tan 2 theta is equal to MD by FD. Let this be equation 2. For paraaxial rays, theta is small and hence we can write tan theta is approximately equal to theta. Let this be expression 1. And tan 2 theta is approximately equal to 2 theta. Let this be expression 2. From expressions 1 and 2, we can write that tan 2 theta is equal to 2 into tan theta. On substituting the values of tan theta and tan 2 theta from equations 1 and 2, we get MD by FD is equal to 2 into MD by CD. Or CD is equal to 2 into FD. Let this be equation 3. For paraxial rays, the 2 points P and D are very close to each other. And hence, we can assume that CD is equal to CP. And FD is equal to FP. Therefore, CP is equal to 2 into FP. This equation can also be written as PC is equal to 2 into PF. But PC is the radius of curvature R and PF is the focal length F. Therefore, R is equal to 2F. Now let us study the images formed by spherical mirrors. following 4 rays from the source are easy to trace and help locate the images formed by a spherical mirror. 1. If the incident ray is parallel to the principal axis, then, after reflection, it passes through the principal focus in the case of a concave mirror, and appears to diverge from the principal focus in the case of a convex mirror. 2. If a ray of light initially passes through or appears to pass through the center of curvature C, then, after reflection, the ray retraces its path. 3. If a ray of light initially passes through or appears to pass through the principal focus F of the mirror, then, after reflection, the ray is parallel to the principal axis. 4. If a ray of light is incident at the pole, then the incident ray and reflected ray make identical angles with the principal axis. Let us place an object AB in front of a concave mirror. Using the rays of light discussed, we can find the image of point B at point B dash. Not only these 4 rays, any ray that emerges from B and incident on the mirror after reflection passes through point B dash. By treating object AB as a combination of many point objects, and by finding the images corresponding to each of these point objects, we can find the image of the whole object AB as A dash B dash. Thus, the image of an extended object has a point-to-point correspondence with the object. Images formed by a concave mirror for different positions of an object are as shown. Similarly, in the case of a convex mirror, for different positions of an object, the images formed are as shown. Usually, the distance of the object from the mirror is denoted by U, and the distance of the image from the mirror is denoted by V. We follow the Cartesian sign convention to measure distances from the mirror and heights from the principal axis. According to this convention, all distances are measured from the pole of the mirror. For example, measurement of the focal length F and the radius of curvature R are measured as shown. Distances in the direction of incident light are taken as positive, and distances measured in the direction opposite to the direction of incident light are taken as negative. For example, in the case of a concave mirror, if the focal length and the radius of curvature is measured from the pole, then the measurement is in a direction opposite to the direction of the incident light. Hence, they must have negative values. On the other hand, for a convex mirror, the values of focal length and radius of curvature must be positive, as these measurements are in the same direction as the direction of the incident ray. Heights measured upward and normal to the principal axis are taken as positive, and the heights measured downward are taken as negative. When object AB is placed beyond C of a concave mirror, an inverted image A' B' is formed. In such a case, the length of the object is positive and the length of the image is negative. With the proper sign convention, we can use a single formula which we will discuss in the next module for all possible cases. The mathematical relationship between an object distance u, image distance v, and the focal length f of a mirror is called the mirror equation. Let us derive the mirror equation for a specific case where the object is placed beyond C of a concave mirror. Let OJ be the object and IG be its image. If only paraxial rays are considered, M must be very close to P, and hence PM can be treated as a straight line. And OJ is equal to PM. Now observe the ray diagram. As triangles IGF and PMF are similar, we can write IG by PM is equal to IF by PF. Since PM is equal to OJ, this can also be written as IG by OJ is equal to IF by PF. Let this be equation 1. Now, observe the two triangles OJC and IGC. Since they are also similar triangles, we can write IG by OJ is equal to IC by CO. Let this be equation 2. From equations 1 and 2, we can write IC by CO is equal to IF by PF. Let this be equation 3. But from the ray diagram, we can write IC is equal to PC minus PI, where CO is equal to PO minus PC and IF is equal to PI minus PF. Substituting these values in equation 3, we get PC minus PI whole divided by PO minus PC is equal to PI minus PF whole divided by PF, which is equal to PI by PF minus 1. On simplification, we get PI by PF is equal to PO minus PI whole divided by PO minus PC. Let this be equation 4. We know that PO is the object distance, PI is the image distance, PF is the focal length, and PC is the radius of curvature. Now we need to apply the Cartesian sign convention to substitute appropriate values for these terms. Note that the object is to the left of the mirror, and hence the light rays are incident on the mirror from left to right. Hence, the direction from left to right is to be taken as positive. Now, on application of the Cartesian sign convention, we can write that PO is equal to minus U, PI is equal to minus V, PF is equal to minus F, and PC is equal to minus R, which is also equal to minus 2F. On substituting these values in equation 4, we get Equation 5. On further simplification, we get UV is equal to UF plus VF. Dividing each term of this equation with UVF, we get 1 by F is equal to 1 by V plus 1 by U. This is known as the mirror equation. This equation is valid for both types of spherical mirrors and is applicable to all positions of the object. It is important to note that, while using the mirror formula, proper use of a sign convention is required. We know that the size of the image formed by a spherical mirror depends on the position of the object. The ratio of the height of the image to the height of the object is defined as the linear magnification and is denoted by m. If h is the height of the object and h dash is the height of the image, then m is equal to h dash by h. Since the two triangles OJP and IGP are similar, we can write that IG by OJ is equal to PI by PO. When a proper sign convention is applied, we get OJ is equal to H and IG is equal to minus H dash. Substituting these values in the above equation, we get minus H dash by H is equal to minus V by minus U. Therefore, M is equal to H dash by H and is equal to minus V by U. Note that the linear magnification M is negative if the image is inverted. And as a consequence, M is negative in case of real images. On the other hand, if the image is erect, M is positive. Hence, M is positive for virtual images. Now let us use the mirror formula and the expression for linear magnification to solve some problems. Example 1. A plane sheet of length 0.1 meter and breadth 0.05 meter is placed at a distance 0.25 meter from a concave mirror of focal length 0.2 meter. If the principal axis of the mirror is perpendicular to the plane of the sheet and passes through one of the vertices, then find the length and breadth of the image formed. Solution. Given that length of the sheet L is equal to 0.1 meter, breadth of the sheet B is equal to 0.05 meter, object distance U is equal to minus 0.25 meter, focal length F is equal to minus 0.2 meter. According to the mirror formula, 1 by F is equal to 1 by V plus 1 by U. This can be written as 1 by V is equal to 1 by F minus 1 by U. Substituting the values for U and F, and on simplification, we get V is equal to minus 1. That means the image is formed at 1 meter from the mirror. We know that magnification M is equal to minus V by U. On substituting the values for U and V, and on further simplification, we get M is equal to minus 4. That means the image is 4 times bigger than the object. Note that the minus sign for magnification M indicates that the image formed is inverted. Now the length of the image L dash is equal to M into L, which is equal to 0.4 meter. And the breadth of the image B dash is equal to M into B, which is equal to 0.2 meter. Example 2. The image formed by a convex mirror of focal length 0.4 meter is 1/4 the size of the object. Find the distance of the object from the mirror. Solution. Given that the focal length f is equal to 0.4 meter and magnification m is equal to 1/4, we need to find the object distance u. F is positive because we are dealing with a convex mirror. Since a convex mirror always forms an erect image, m is taken as positive. We know that m is equal to minus v by u. According to the mirror formula, 1 by f is equal to 1 by v plus 1 by u. This can be written as 1 by v is equal to 1 by f minus 1 by u. Or 1 by v is equal to u minus f by uf. Implies v is equal to uf by u minus f. Or v by u is equal to f by u minus f. This can be written as minus v by u is equal to f by f minus u. Or m is equal to f by f minus u. Substituting the values for f and m in this equation and on further simplification, we get u is equal to minus 1.2 meters. Note that u is negative because the object is always in front of the mirror. Example 3. When a concave mirror is used, the magnification is found to be 4 times greater than when the object was 0.25 meter from the mirror as it was with the object at 0.4 meter from the mirror. If the image formed is real in both cases, find the focal length of the mirror. Solution. Since the images are real, both the magnifications are negative. Let the magnification be minus m1 when the object is at a distance of 0.4 meter and minus m2 when the object is at a distance of 0.25 meter. On rewriting the mirror equation, we have m is equal to f divided by f minus u. Then, m1 is equal to f divided by f minus u1 and m2 is equal to f divided by f minus u2. Now we can write minus m2 is equal to 4 into minus m1. That can also be written as m2 is equal to 4 into m1. On substituting the values of m1 and m2 from the above equations and on further simplification, we have 3f is equal to 4u2 minus u1. When the values of u1 and u2 are substituted, we get f is equal to minus 0.2 meter. How does one solve the problem if the second image is a virtual image? If the second image is virtual, then M2 is positive. Then we will get the condition as M2 is equal to 4 into minus M1. And by substituting the values for M1 and M2 and on further simplification, we get f is equal to minus 0.28 meter. Can we solve the same problem if both the images are virtual? To get virtual images, in both cases, the object must be between F and P. As the object is moved from F to P, the size of the virtual image decreases. As such, the condition M2 is 4 times M1 cannot be fulfilled.